Greetings, fellow explorers. This is Tony with Fount Systems Network, and we're here in pursuit of low-carbon innovations for seawater desalination. The episode today is an overview of desalination technology and its environmental impacts. I did a fair amount of research online on YouTube, for example, and I didn't find any single presentation that showed what I would like to share. So I've put together some original content here that uses existing YouTube resources as well as academic research, and I look forward to sharing it with you today. If you're new to Fount Systems Network, please click on the link here. This is our work plan, so you can get a sense of where we are in the process. If you like what you see here, don't forget to like and subscribe. Let's get started. So here's the format. I would like to present a video that shows a desalination facility and what the major features in that facility are. Then we'll look at environmental impacts, both from brine discharge, industrial chemical effluents, and carbon dioxide. And then I'll present some original calculations and visualizations that help us kind of get a handle on the scale of the environmental impacts. So we can get started with our video of the animation of the facility here.
Improving access to resources while preserving and replenishing those resources is what we do at Veolia. In many areas, there is not enough fresh water to satisfy demand. Each day, we produce fresh water from seawater desalination plants to supply one of the resources that industries, communities, and the people do need. Hybrid desalination plants combine thermal desalination, meaning distillation, and membrane desalination, meaning reverse osmosis. These are the most efficient technologies available today. Here's how and why at a glance. We extract seawater several hundred meters offshore. Gratings in screens block large floating objects and keep sea life out. We desalinate some of the seawater by distillation. This technology reuses steam from a close-by thermal power plant that would otherwise be wasted. The steam evaporates the seawater to separate it from the salts and other substances. The steam then moves into cooled pipes and the fresh water condenses. The rest of the seawater heads into the reverse osmosis desalination unit. As there are algae and other suspended matter in the water, it needs to be pre-treated. A coagulant binds these particles. Small bubbles lift them up to the surface, and we skim them off. The clarified water then goes through layers of sand and anthracite that retain the finer particles. At this point, the water contains nothing but salt. We microfilter the saline water, then treat it by using reverse osmosis technology. We pump the water through extremely fine semi-permeable membranes at very high pressure. These membranes hold back the salts and let the water through. This water is then collected in a central pipe. 2 liters of seawater yield 1 liter of demineralized fresh water and 1 liter of water containing twice as much salts as before. We return the brine to the sea without disrupting the natural environment. At the end of the treatment, we add mineral salts to make the water suitable for consumption. We analyze the quality of the water and adjust if necessary, at every step in the treatment. Hybrid desalination produces fresh water in areas that lack it and uses available energy smartly, resourcing the world.
So there's a good introduction. I thought that animation described the interiors of the facilities pretty well. I'll post a link to that in the resources below, and then we'll move next to our environmental impact section. For our first section here on environmental impacts, we're going to look at brine, effluent, and then we're also going to look at industrial process chemical effluent. When a reverse osmosis facility takes in seawater, it extracts pure water, and then what's left is a highly concentrated solution of everything you don't want in your pure water, and then that gets pushed out back into the ocean. So let's look at an animation of that here.
Because they're not just outputting clean, desalinated water. They're also producing huge amounts of hyper salty water called brine as a byproduct.
Seawater desalination plants that use reverse osmosis typically operate at a 50% efficiency, in that if you take in 2 gallons of seawater, you're going to produce 1 gallon of fresh water and 1 gallon of hypersaline brine.
It's a fixed volume of salt that I'm trying to remove. Whether I put it in half a gallon of water or a tenth of a gallon of water, it's still going to be there, and it's just going to be much more concentrated.
As desalination efforts grow, it's not clear what should be done with these huge amounts of brine. Globally, right now, we're producing over 37 billion gallons a day. Most brine is in one way or another emptied back into the ocean, but because it has a much higher salt concentration than regular seawater, it has the potential to, among other things, sink to the seafloor and wreak havoc on the plants and animals found there. In addition, because these facilities are taking in millions of gallons of seawater a day, the intake itself could destroy local marine life.
So the video provides a good kind of visual of the issue, and I want to look a little bit more at some academic research that supports that and helps us get a little more detail on that. Here's some research that shows environmental impacts from brine and chemical effluents. These two professors teach at Yale and at Notre Dame, and this is the future of seawater desalination, energy technology, and the environment. I will scroll down here to the section of interest for us. The elevated salinity of seawater reverse osmosis brines and the chemicals used in pretreatment and membrane cleaning protocols also pose environmental risks to organisms when discharged into the marine environment. The main chemicals that RO plants discharge are antiscalants, coagulants, and cleaning chemicals. So you have both the brine that is left over from the seawater that gets put back in the ocean. Then you also have the industrial chemicals that support the seawater purification processes that end up in that brine as well. There are a few solutions that the authors summarize here. One, you can dilute the waste stream. So here we have dilution is the solution to pollution. You can discharge the plume in a dispersed manner through some kind of diffuser system. You can discharge it at a location in the ocean that is not as environmentally sensitive as, say, an estuary. I don't know if there are any being discharged into any estuaries. I just want to use that as an example. Here they're describing membrane-based pretreatment methods. So I'm assuming this is another water purification plant, which begs the question of what happens to the effluent from that plant then. And then here they're suggesting more efficient technology that doesn't require as much inclusion of industrial chemicals for the processes. At the end, the authors acknowledge that there's considerable uncertainty regarding the environmental impacts of desalination, meaning there's not enough research. And they make the optimistic statement that environmental impacts will not be substantial if appropriate measures are implemented. And so you can draw your own conclusions from that summary. Let's talk about carbon dioxide emissions. As you probably recall from background 2 on global warming, seawater desalination is a very energy intensive and therefore a very carbon dioxide intensive process. It takes a lot of energy to get fresh water from salt water, and that energy is generally coming from electricity, not exclusively, and we'll get into that further. That electricity is created from combustion of fossil fuel sources. So I want to look at the desalination, the carbon footprint of desalination for the UAE, for the United Arab Emirates, and for 2 reasons. One, they rely a lot on desalinated water in that region, and 2, there's pretty good data available. So let's take a look at some source literature here. This is a research article from the Applied Energy Conference, Calculation of Carbon Footprints for Water Diversion and Desalination Projects. And if we scroll down here, we can find some useful source data, which I will in turn, I'm going to use this data and I'm going to interpret it. So let's take a look at what I've put together here. I want to figure out what the carbon footprint is of desalination in the UAE in terms of quantities of CO2 generated. So here we have the chart. This is all the data from that article. I'll start by saying that we have three techniques for desalination: multi-stage flash, desalination, multi-effect distillation, and reverse osmosis. Multi-stage flash, you can see, is what they rely on heavily. So it looks a substantial portion of their capacity is in this technique. Multi-stage flash generally uses waste heat from energy or electricity generation of power plants. And so we saw a little bit of that in the Viola video earlier. But we can see also that it's very carbon dioxide intensive. We can also see that multi-effect distillation generates less CO2. Reverse osmosis is somewhere in the middle. So taking all of these together, we get almost 16 million kilograms of CO2 generated per day if they're operating at capacity. Annually, that's about 5.8 billion kilograms. And then let's assume they're not operating at capacity all the time in the UAE. Let's say over the course of a year, they're averaging about 80% capacity. So we can suggest with that assumption that we're at 4.6 billion kilograms of CO2 being generated every year from the UAE for seawater desalination. So what does 4.6 billion kilograms of CO2 look like? I wanted to do a visual kind of representation of that because it's such a large quantity, it's just hard to imagine. So I thought, let's imagine all of that CO2 as sand. Everybody has played with sand, handled sand, built sand castles on the beach. You know how heavy it is. If you took 2 5-gallon buckets of sand, you'd have a hard time holding it off the ground. Each of those buckets, it's about 60 or 70 kilograms, but that still doesn't get you anywhere close to how big the pile of sand would be. So I thought I would start with this image, which is Cowboys Stadium in Dallas, Texas. I don't have anything against the Dallas Cowboys. This is just known as a really big stadium, and you can kind of put yourself in it and get a sense of how large that pile of sand would be. So here's the stadium empty, and then here we have approximately the pile of sand that would fit in that stadium. I mean, it just about fills the stadium. It's a pile of sand about 290 meters in diameter at the base. So really, almost enough to fill that stadium. So that'll give you a sense of how much sand there is. It's certainly a lot of 5-gallon buckets, but let's look at it another way. Let's look at it as just pure CO2 gas. If we took all of that mass of CO2 and we represented it relative to the Dallas Cowboys Stadium, here's what you'd have. This is Dallas Cowboys Stadium in the middle of the satellite image here. And then this cylinder represents the volume of CO2 gas that is generated every year by the UAE for desalination purposes. And it's about 1 mile in diameter and about 1 mile high. So I don't want to pick on the United Arab Emirates. If we reference the article that I shared with you earlier, the UAE accounts for 14 or 15% of all of the desalination capacity around the world. So you could take, using a rule of thumb, what I shared with you as far as quantities of CO2 and multiply by 7 to get a global planetary burden of carbon dioxide emissions. So that's it for this presentation. This is introduction to seawater desalination. You got a brief tour of a desalination facility. We looked at environmental impacts from brine and industrial chemical effluents, and most importantly, for our Fount Systems pursuit, the burden of carbon dioxide emissions. Thank you for watching. If you like what you see here, please like and subscribe. Remember, keep exploring, keep growing. I'll see you next time.